Welcome back. This video is part 2 of a lecture series on chemical kinetics. The first part dealt with average reaction rate, instantaneous reaction rate, and the stoichiometry and reaction rate. Today what we're going to focus on is rate laws and the determination of rate laws through experimentation. So what is a rate law? You've got to speak the language here. And a rate law is an equation that relates the concentrations of the reactants. Notice we're not focusing on the products like we did when we did stoichiometry of reaction rates in the last part. So the reason why we don't generally focus on the products is that the reaction starts and reactant A and B become products C and D. And once products C and D form, this reaction, if it's reversible, could reform A and B. So it gets a lot more complicated looking at reaction rates of both reactants and products. So a rate law focuses only on the reactants. And the way we write a rate law is it's the overall rate is equal to the rate constant times the concentration of A. When we have brackets, we're talking about molarity units, and times the concentration of B. And these are raised to exponents x respectively for A and y respectively for B. And these exponents can only be determined experimentally. That's really important. That in a rate law, the exponents or the powers or the orders, that's the word we usually use, orders, can only be determined experimentally. And the rate constant, the only thing that will change a rate constant is temperature. I mean, that's what we need to focus on there, is that the only thing. So we're assuming most of the time when we do a series of reactions to determine the orders with respect to A and B, that the temperature remains constant. So keep that in mind, especially for those of you taking the lab and are going to be doing an experiment determining the orders. So they didn't show the reaction here. They assume you remember the reaction from the last part, but it was bromine reacts with formic acid and forms the bromide ion, and I forget what else. But when we look at just the reactants, the rate law for that reaction is, again, the rate constant times the concentration of the bromine times the concentration of the formic acid. And through a series of experiments, it was determined that it's first order with respect to the bromine and it's zero order with respect to the formic acid. Now, we know that 10 raised to the 0 power is equal to 1, so we don't see formic acid in the final expression here because formic acid raised to the 0 power is 1. Doesn't mean it's not important. It does need to be present for the reaction to happen, but it's not got a relationship of concentration versus rate, that direct concentration, the direct relationship that you see here. So we would speak the language here. This is first order with respect to the bromine, which they have a typo there, zero order with respect to the formic acid. And when we add the 1 plus the 0 together, the overall order is first order. So that's where this gets a little tricky sometimes. If you don't see it in the expression, then it's zero order over here, okay? And so we are just looking at this one, so we know this is 0. And so the first, the reaction overall is first order. So just keep that in mind. Make sure you look at that. So rate laws are determined by the initial rate. It's an instantaneous rate, which we talked about the last time. Instantaneous rates are measured by a line tangent to the curve, and then we get the rise over the run, or the change in y over the change in x. and we determine the instantaneous rate. So again, if you haven't seen part 1, we defined instantaneous rate in that video. And the reason why we want those initial rates, we want to capture most of it at the initial surge of the reactants going to products, because again, if the products are formed and we start seeing the reverse, that's going to affect the concentrations. So we generally look for we measure rate loss with the reactants at their initial rates. So what does that look like? Well, it looks like this. So we have a reaction, so make sure you have a balanced chemical reaction. So here we have fluorine reacts with 2 moles of chlorine dioxide, and we get 2 moles of fluorochloro dioxide. Here's our 2 reactants, and so we have the rate law is rate equals the rate constant times the concentration of the fluorine raised to some exponent x, and times the concentration of the chlorine dioxide raised to some exponent y, which we call orders. Okay, so what is the order with respect to the fluorine? That's what we need to solve for x. What is the order with respect to the chlorine dioxide? And we have y for that exponent, which we would call the order with respect to the chlorine dioxide. So we're going to do a series of experiments here. So we assume, here's the big assumption, we assume that the temperature remains constant through the course of this reaction. Why does that have to be? Because temperature affects the rate constant. We saw that in the last video. So we assume the temperature is remaining constant, and we're looking at the dependence of the reaction rate on the reaction concentrations, and that's what we're doing. So we have a concentration of fluorine at 0.10 molar. We have chlorine dioxide at 0.010 molar. And the initial rate of the reaction is 1.2 times 10 to the negative 3 molarity units per second. All right, so then we quadruple the change of the chlorine dioxide. So it's 4 times, right? Quadruple. We keep the fluorine constant, and we look to see what the rate change is. So the initial rate goes from 1.2 times 10 to the negative 3 to 4.8 times 10 to the negative 3. And hopefully you can see that's a 4-fold increase in the rate. Now, if you can't, it's okay. You just need to divide this number by that number and divide 0.04 by that number. So let me show you what that looks formally. It looks like, well, let's look at the other one. Let's look at the other one, and it's got it down here. All right. So then if we look at experiment 1 and experiment 3, we doubled the concentration of the fluorine, doubled it. And if we look at the relationship between the initial rate of experiment 1 and the initial rate of experiment 3, we can see 2.4 divided by 1.2 times 10 to the negative 3 is double as well. So here's what I want you to, this is the important part right here. So on one side, we don't know what x is here. Okay, we don't know what this x is. So that's what we want to solve for. So what we do is we divide experiment 3 by experiment 1. You say, why do you divide 3 by 1? Why not 1 by 3? You can do it that way too, but most people like to work with whole numbers instead of fractions. And so we generally divide the largest by the smallest. So when we divide 0.2 by 0.1, we get 2. So we get 2 to the x power. All right, so just keep that in mind. I wish they would have done that. So we got 2 to the x power equals 2.4 divided by 1.2 gives me a difference of, or a ratio of 2, I should say that. All right. So then how do you solve this? You've got 2 to the x equals 2. So here's a little bit of mathematics, right? So you got 2 to the x equals 2. Now this one's easy. you can tell me right now that x has to equal 1. Everybody can look at this and say, oh yeah, I know x is equal to 1. But what if it isn't that easy? How do you mathematically solve for x here? So what you do is you have x equals the log of 2, which is equal to the log of 2. And then you would find out that x equals 1. All right, so technically that's the way you do it to get the exponent. That's why we have logarithms. It's the inverse of the exponent. And if you don't remember this, if you don't remember how to use logarithms, make sure you look at the appendix in the back of the book. There's a whole section on it. And I do find in Chem 180, one of the reasons why students don't do well is they don't know how to freely manipulate exponents and logarithms. So make sure you spend the time doing that. If you need a little brush up on that, just go back to the appendix and look at that, and I think that'll help. So what we now know is the fluorine, with respect to the fluorine, the order is 1, and we don't put a 1 there. If it's in the expression, we understand it to be 1. Okay? So that's the first part. The next part is we have to determine with the order with respect to the chlorine dioxide. So again, which experiments are we going to use? We need the experiment where the fluorine is held constant and the chlorine dioxide is changing. So you wouldn't use like experiment 2 and 3 to do the comparison, because in 2 and 3 the fluorine's changing and the chlorine dioxide is changing. So that would be a no-go. So again, which experiments are we going to use? 1 and 2. All right, so when we look at 1 and 2, we're going to take the larger experiment 2 for the chlorine dioxide and divide it by experiment 1. Again, this is held fixed. This is unchanged. That's important. So any change in the rate is directly reflected by the concentration change of the chlorine dioxide. So we're going to take 0.04 divided by 0.01. And then the rate is 4.8 times 10 to the negative 3 divided by 1.2 times 10 to the negative 3. And again, we get a value of 4 here, and we get a value of 4 here. And so what we're saying here is for the chlorine dioxide, it's 4. And it's raised to the y power, and that equals 4. So again, this one's easy. You know that y has to equal 1. And so we know it's first order with respect to the chlorine dioxide. So our rate law is the overall rate is equal to the rate constant times the fluorine concentration times the chlorine dioxide concentration. It's first order with respect to the fluorine. It's first order with respect to the chlorine dioxide. And it's second order overall. Second order overall. Now that's going to be important later on. Like, it's important to know what the order for the reaction is. It's going to give us an insight to the reaction mechanism. So this is second order overall. First order with respect to fluorine. First order with respect to chlorine dioxide. Second order overall. All right, so then how do I determine the rate constant for this reaction? So if I manipulate the rate law to solve for K, so let's just rewrite that up here. If I have rate equals K, first order with respect to the fluorine, first order with respect to the chlorine dioxide. There's my rate law. I want to solve for K. So K equals the rate divided by the concentration of the fluorine first order, concentration of chlorine dioxide first order. I don't care which one of the experiments you choose. You can choose any one of the 3 that was on the previous page and plug these values in, their initial rate divided by the concentrations, and you should get 1.2. In this case, it's let's look at the units. This is really important. So it's molarity in the numerator, and it's molarity squared in the denominator, and then the seconds here is in the denominator. So one of these molarity units cancel out, and that gives you molarity in the denominator. So in the end, what we have is 1 over molarity units seconds. And the way you're going to see it published is like this, with the -1 power. It's easier to do that than trying to line up these numbers under a bar. And so you're going to have to get used to, when you see molarity to the -1 power, that means the molarity is in the denominator and the seconds is in the denominator. You go, why is this important? Because if you know the units for the rate constant, you know the overall order of the reaction. All second order reactions are going to have these units. So the units for the rate constant clue you in as to what the overall order of the reaction is. It's super important that you know those. So like if it's first order, let's do that. Let's say, let's go back to this one. If rate equals K times the concentration of the bromine, all right, you know that, so K is equal to the rate divided by the concentration of the bromine. And you know rate is in molarity units per second, and then this is in molarity units, the bromine concentration. The molarity cancel out, and you get seconds to the -1 as your answer. So if I see seconds to the -1 as my rate constant, that tells me the order of the reaction is first order. And so that's what it looks like for first order. For a second order reaction, where this is second order overall, all right, one for this, one for this, then the second order overall is going to have those units or these units. Okay, so just keep that in mind. It really helps. You say, a lot of times I hear students say, I didn't have enough time to answer the quiz questions, or I didn't have enough time to answer the test questions. And the reason why is there are problems on the quiz, on the test. All you're supposed to do pretty much is look at these units, and from the units you can determine the order. And you don't have to do all the calculations. So just keep that in mind. All right, so let's look at another example. So this is a general form, okay? So we have A reacting with B, form products C and D. And, I do see this a lot. A lot of students think the coefficients are these orders. No, the only way we know what these orders are is through experimental data. Now, I agree the coefficients can be those orders, especially if we're doing we know what the fundamental rate determining step is, but they still have to be determined experimentally. So don't fall into the trap that whatever this is X and whatever this is Y. It doesn't work that way. Okay, so let's look at this experiment. And this one, what we're looking for is, if I want to look at the order with respect to A, I want A to change, and I don't want B to change. If they both change, you can't determine it. So B is staying constant here. A is changing, and then we look and see what the change in the rate is. Now, again, you could do this formally. You could sit there and say, you can say, you can say formally, you can say it's K times A to the X power times B to the Y power. And A is 0.10 molar, and so you could divide that by, let's make this the 0.2 molar to make it easier. And then we could say K divided by A, which in the first case it's 0.10 molar raised to the X, and this is B raised to the Y power, and then you would say 4.2 times 10 to the -4, and you would divide that by 2.1 times 10 to the -4. That divides out, and then you have 0.2 divided by 0.1. So 0.2 divided by 0.1 raised to the X power equals 4.2 times 10 to the -4 divided by 2.1, which is 2. And so what you end up getting is 2 raised to the X power equals 2. And so you know that X is 1, and you get that for the answer. So the reason why I spelled it out is I want you to get good enough at this that you could just look at this and go, oh yeah, this one's easy. We double the concentration. We double the rate, the initial rate of the reaction. I know it's 1-to-1, and I'm done. I'm done with that. I already know that the rate, the order with respect to A is 1, and that's how quick it can be done. But if you get stuck, this is formally how you do it. You do it in steps like this. Where I see students get into problems is, again, if this isn't a nice like 1, 2, or 3 for the order, then you're going to have to say the x of log whatever, the concentration, equals whatever this number is, and solve that way. It makes it more complicated, but I don't want you to say I can't do it. All right, so then I do see this as a mistake sometimes. When you're looking for the order with respect to B, you have to see, you got to choose the experiments that A is not changing and B is changing. All right, so if you chose to compare 2 and 3, that wouldn't work because A is changing in concentration and so is B. So we choose 1 and 3, and here's what you see. You see that we doubled the concentration of B, and then this one's different. We quadrupled the rate of reaction. So what you have here is you have 2 raised to the y power equals 8. Because it's 2 here, from here, 0.03 minus 0.015 is 2. Divided, yeah, what am I saying? 0.030 divided by 0.015 is 2 raised to the y power equals, oops, I did this wrong. See, that's why you got to write it out. Quadrupled, all right? So y must equal 2, okay? All right? So that's, I think it's important you write this stuff out, because see, I would have made a mistake there, and then I was thinking about that's what's happened. So it's 4, and so y equals 2. So the next thing is, you now know that it's first order with respect to A, it's second order with respect to B, and so the overall order is 3. And notice the units are different here. Notice the units are different. You're getting molarity times molarity squared. That's molarity cubed in the denominator. One of those molarities is going to cancel out with that one, and we'll get molarity squared left in the denominator and seconds in the denominator. So it's 1 over molarity squared units, seconds. So that's why you have a -2 here and a -1 here. All right? For the rate constant. So once we get finished and we've got our rate law, I can plug in any of these concentrations and these initial rates, the respective initial rates, and determine the rate constant. And again, it should be pretty much the same number regardless. I mean, it might be plus or minus 1, the least significant figure or something like that. But it should, because that's why this is called a rate constant. It should not change through the course of the reaction. And again, how do we ensure that it's not going to change through the course of the reaction? We assume the temperature is held constant for all 3 experiments. Neat stuff. It really is. It's cool stuff. This is, you go, why do I need to know about rates and orders and so forth? When you start to try to determine, the mechanism of why something happens, how a reaction happens, how a biological process happens, rate laws are the way to do that. So here they have it in a table. I want you to know this table. This is how you quickly get through some problems. If the overall order is 0, that just means rate equals K, right? There's no first order. It's just rate equals K. There it is. Then there's my units. There's my units for first order, second order, and third order. Let me just say third order is pretty complicated. Most reactions that happen are first or second order. There are some that are 0 order, but most are first or second. But you need to know, we will deal with some rate 0 rate orders, overall rate orders. All right, so here's the rules. The following 3 important things to remember about a rate law. The exponents in the rate law must be determined experimentally. We test on that. We want to make sure you know it comes from experimental data. It is not the stoichiometric coefficients. All right, that's what most students do. They think it's the balanced chemical equation is stoichiometric coefficients. Understand why they think that, because if you talk about equilibrium, we will look at the stoichiometric coefficients. This is not equilibrium. This is kinetics, all right? Comparing the changes in the individual reactant concentrations with changes in the rate shows how the rate depends on each of the reactants concentrations. So we've done that. That's why you have to have a series of 3 experiments for 2 substances. If you have more substances, you're going to have more experiments. And then the last rule, reaction order is generally defined in terms of reactant concentrations rather than product concentrations, because once products are formed, those products can revert back to reactants, thus complicating the rate law. All right, so here's your chance. So it says the gas phase reaction of nitric oxide with hydrogen at 1,280 degrees Celsius. And the reason why they put the temperature in there is it has to remain constant through the course of the reaction. From the following data collected at 1,280 degrees Celsius, they're really stressing that, hey, the temperature is not changing through the course of the reaction. What they want to know is, what is the rate law? Well, that's easy. You can just say rate equals K times the concentration of the nitric oxide raised to some power X times the concentration of the hydrogen raised to some power Y. Now, we have to determine what those are. So the rate constant, including the units, and then they also want to know the rate of reaction when nitric oxide is 4.8 times 10 to the negative 3, and hydrogen is 6.2 times 10 to the negative 3 molar. All right. All right, so stop here. Well, you actually have to look at the next slide, right? Because we've got to have data, right? So here's my data. All right, so again, we can't determine the orders with respect to nitric oxide or hydrogen until we have some data. So here's our data. So what I want you to do is write down what was on the previous slide, write down what's on this slide, and see if you can solve this problem. And if you can, you're in good shape. If you can't, you just need to try more problems. There's ones in the book. They go through all the steps that we just went through before. And I generally think it takes at least 3 to 5 of these to get a feel for it. Okay? So stop right here, do it on your own, and then I'll talk about how we go about it here. All right. So you're back. So what we want to do, let's just do this right off the bat. We know that the rate equals the nitric oxide, well, let's put in our rate constant, nitric oxide raised to some power X, and then the hydrogen raised to some power Y. And that's what to get the rate law, we have to know what X and Y are. So, looking at the experiments, which experiments are you going to choose to measure how concentration of nitric oxide affects the rate, the initial rate? So I would look at, let's look at this right here. We can see that nitric oxide is changing. Hydrogen is held constant. So any change in the rate of the reaction is due to the nitric oxide concentration changing. So if I take 1.0 times 10 to the negative 2 raised to the x power, and I divide that by 5.0 times 10 to the negative 3 power, and then I set that equal to 5.0 times 10 to the negative fifth divided by 1.3 times 10 to the negative fifth. And again, I didn't put the hydrogen here, and I didn't put the rate constants. Those things aren't changing. Those divide out. To simplify this is what I wrote down. Then what we get is, let's see what we get on the next page. I mean, here we know it's 2, right? This is going to be 1 divided by 2 because this is 0.5. So it's 2 on this side. And then what are we getting on the other side? 4, pretty close to 4. And you're going to see that. It's not going to come out nice, perfect numbers. It is going to be experimental data doesn't fit the numbers precisely. So it is, they say, approximately 4. So we have 2 raised to the x equals, let's just do that real quickly. What is 5 divided by 1.3? 3.84. All right, 3.84. All right, so then if you want to, you say, man, that doesn't look good. 3.84, is it 4? So just do this. Take x times the log of 2, divide by, and then over here we have the log of 3.84. And so let's do that. Let's see what that equals. So take log of 3.84. And we're going to divide that by the log of 2. And we get 1.94. All right, 1.94. And then to the ones place, it's 2. All right. So there we go. So then you do the same thing for the other side, right? So we want the hydrogen to change, but we don't want the nitric oxide to change. And we look at the change in the initial rate. So comparing 2 and 3 shows the hydrogen. All right, I'll go with that. All right, so here it is for the first one, which we already did. X equals 2, so it's second order with respect to the nitric oxide. For the hydrogen, you have 4 times 10 to the negative 3 divided by 2. We see about a double in concentration. So 2y equals 2, so y equals 1. So it's second order with respect to the nitric oxide and first order with respect to the hydrogen. And overall, if you wanted to know what the rate constant is, we can plug that in, which is, this asks for that as well. So we can plug any of our experimental data into solving for K, and we would get 2.6 times 10 to the second. And again, we know we've done this right because it should be third order, and that's the units for the third order rate constant. All right. Once we have the rate constant, we can take any experimental data concentrations, plug that into the rate law, multiply it by the rate constant, what we determine here, and we can determine the rate of the reaction. That's what's cool about it. Once you solve for the rate law, you know what the orders are, and then you know what the rate constant is. We assume at that particular temperature, we can plug any concentration in here, and we can get the rate of the reaction. That's ultimately what we're looking for, is that once we establish the rate law, and we know what the value of the rate constant is, plug any concentration units in and get the rate of that reaction. And that's the power of it. All right, let's see. Let's continue on. I thought about stopping right here, but let's just go on and talk about first order and second order reactions, and then we'll stop, okay? So we've been talking about overall reactions, overall order of the reaction, and we have first order reactions and second order reactions, and we have third order reactions, and we have zero order reactions. And this is what this section is going to be about, is first and second order. So here's how simple it is. And if you've had calculus, this is going to be really easy for you. If not, you're going to have to memorize some here, okay? So we have A going to B, A going to product. So this is kind of like what you see with radioactive decay. Just A falls apart, right, and it forms a product. So it's just dependent on A falling apart forms a product. And so from our the first part of chapter 14 on kinetics, we would say the rate equals negative the change in concentration of A over change in time. And remember, the negative cause A is decreasing over time. And so we have to have a positive overall rate. So that's what the correction factor for this is. All right. So a rate law for this would be rate equals K, the rate constant, times the concentration of A. And it's a first order reaction. So we know that there's a 1 here, but we don't draw it. So we know it's first order. So we set these two equal to each other. And then here it is. Here's all that calculus you've had. This is the change in concentration over the change in time equals Ka. And we do an integration of this, And so when we integrate this, that T comes out here, and then we get the ln of A at some time T divided by A initial. So if you know how to do the calculus from here to here, you're in great shape. That's kind of what, that's why you take calculus. You're going to be able to do that. If you don't, you're just going to memorize that equation here. This is the first order equation. All right, you have to memorize that. Okay. You go, why do I need to know this? Well, you can see right now we've got some variables. We've got what is the final concentration at the end of the reaction, what is the initial concentration, and what is the time that passed through that reaction. So that's what we're looking at here. So let's show you how it works. It says the decomposition of hydrogen peroxide is a first order. So it means that you write the rate law for this, you're going to get rate equals K times the concentration of the hydrogen peroxide to the first power. The rate constant for the reaction is given, and you know it's first order right there. If you see the seconds to the -1 for the rate constant, you know it's first order. Starting with an initial concentration of 0.75 molar, determine the concentration of the hydrogen peroxide after 3 hours. How long will it take for the hydrogen peroxide to drop to 0.10 molar? All right. So these are great questions. You want to stop here. You want to back it up a slide. I'll write it right here. All you're going to be doing on these problems is manipulating this equation. Ln, concentration of A at some time, in this case it's going to be 3 hours, and we'll probably change that to seconds, over initial concentration, which was given, all right, initial concentration, equals negative KT, okay? So see if you can solve for these. Stop here, see if you can plug it in, solve for that, manipulate the ln function. Now, if you can't, you need to go back to the appendix and look at logarithmic functions and how to manipulate them. I think that's what causes a lot of students to mess up on kinetics, is they're just not real comfortable with manipulating the logarithms, in this case the natural log. All right? All right, we'll come back. We're going to plug this in. We're going to see what we have. So again, organize your data. This is A naught, or in this case, hydrogen peroxide. We know 3 hours have passed, so time equals 3 hours. And if you want it in seconds, then you're going to have to change 3 hours to seconds. Do they give us a... Yeah, and we do need it in seconds. I was like, how do you know you have to change it? Because I know you have to change right here. This is in seconds to the -1 power. So you're going to take 3 hours, and you're going to say there's a 1 hour, 60 minutes. And then you're going to say 1 minute is 60 seconds. All right. And you go, why do we have to do that? Because that's what the units for the rate constant are. That's what's going to drive that. Okay, so let's go on. So here we have it. We have the concentration that we're trying to find. The initial concentration was given. That's the rate constant. Don't forget the negative. This is where students make a mistake too here. If you're memorizing it, this is the most common missed part right there, is that negative symbol. Then we have the rate constant, which was given. And then we've converted the 3 hours into seconds. And again, why does that have to happen? Because that's seconds to the -1 power. So we plug in the data, and we get this ratio of that to 0.75 equals, and you go, what's going on over here? Well, this rate constant times the time gives us this number here. Here's where you get into problems if you don't know how to use your logarithms. What's the inverse of the natural log? It's e. And so we take the inverse natural log of both sides, and let me do it this way, down here. So we get e raised to the ln of this, so that goes away, and we get the concentration of the hydrogen peroxide over the initial concentration equals e raised to the negative 0.1944, right here. When we do that, we get this number here. And so now, to solve for the hydrogen peroxide, we multiply both sides by 0.75 molar. And there's our units. There's why we have the units here, and we get 0.62. So does that make sense? Always see if that makes sense. If you initially start at 0.75, and your final better become less than that, because you know it's decreasing over time. The concentration of A, in this case the hydrogen peroxide, is decreasing over time. So if you get a higher value here than 0.75, what it generally indicates is you forgot to put the negative sign in there. You forgot it here, or you forgot it here, or there. So if you get a number that's greater than what you started with, that's probably why you made a mistake. All right? Like that problem, you're going to see it on the quiz, you're going to see it on the exam. It's that important. Make sure you can solve that type of problem, along with the next type of problem. So you go, why do I need to be able to do it this way? Well, a lot of times we want to know, like when we're doing carbon dating and things like that, we want to know how much time has passed on carbon dating to figure out how old the object is that was once living, breathing, right? So here we know what the concentrations are. We know what the rate constant is because we're assuming that's not changing through the course of time. And so we're trying to solve for the time. So we manipulate the equation. We take the ln of this over that, and we get this number here. Make sure you know it's negative, because you take a number and you divide it by a larger number, that's going to be a number less than 1. So that, therefore, there better be a negative here for this part. We set that equal to kt here, and we're going to solve for time. So we take the negative 2.015 divided by the negative 1.8 times 10 to the negative fifth, 1 over seconds, and the negatives, they become unity there. This seconds, the way you remember to think about this seconds to the negative 1 is seconds. It's 1 over seconds, so that seconds is up here in the quotient, because something in the quotient of the quotient is in the numerator. And so we solve for this, and we get 1.12 times 10 to the negative fifth seconds. Nobody likes to deal with these numbers, so a lot of times we do change it to hours or days or whatever it takes to make this number manageable. And so if you convert this to 60 seconds is 1 minute, and then 60 minutes is 1 hour. And then you need to read the question carefully, because sometimes they ask for it in hours or days or years. So read the question carefully to see what they're asking for. All right. We're going to stop here. I think that's long enough. We're at 44 minutes. I'll talk about second order reactions. We'll talk about let's do this. Let's do this before we start. I thought this was the second one. No, let's do this. So here's the equation we've been using. This can be turned into a line equation. So a line is y equals the slope times x plus the y-intercept. All right. So if you don't remember line equation, you need to know this. Y equals mx plus b, where m is the slope. Okay. So we manipulate the equation into a line equation, and we get this equation here. The y value equals the slope times the time that's passed times the initial concentration, which makes sense, right? The initial concentration is where the value is 0 in the y-axis, all right? Initial concentration. Because we're looking at concentration over time. So you go, why do I need to know this? Because you should be able to, once you plot data, you should be able to tell me that it's first order. So if we have a rate, which is first order, so we've seen this one before, rate equals constant, the rate constant times the bromine concentration to the first order. If you just plot concentration versus time, we get a curve going downward, which makes sense. You initially start with a high concentration of the reactant, and then at the final measurement, we see that the rate has the rate's decreasing, and the concentration is decreasing. All right. So here's how we know it's first order. If I plot the rate versus concentration, then I'm going to get a positive sloped line. Okay, as the concentration of the bromine, the reactant increases. There's more collisions per second, and so therefore the rate will increase. So the higher the concentration of bromine, the higher the rate is going to be. That makes sense. I hope that makes sense to you. So when we look at that equation, let's go back a slide. You can see that the higher the concentration, so this is y equals mx plus b, that's the line slope. And so we're going to get, if I plot, well, let's do it. I think they're going to show us that. Surely they're going to show us a picture of that. So here's what they show. They're going to show you plotting pressures, which we can do instead of molarity units versus time. We can do a plot here. Here is what I want to show, is that the slope is actually negative. And you go, why is it negative? Because what we have here is the ln of the pressure, and it could be the molarity if you want to do that, equals negative kT plus the ln of the pressure at time 0. So here's my y, here's my mx plus b. Notice the k is negative here, and so the slope should be negative here. This indicates it's a first order reaction. So as time progresses, we see the pressure drop, and so we get a negative slope line. So the slope of this line, the rise over the run, if you do that, you get k. You get the value. So it's negative, and then you get the k value, which is negative. And so you can determine the slope of the line, or you can determine the rate constant. And the rate constant should always be a positive value, right? So you get the slope of the line. That'll give you a negative value for k. When we plug it into this, we're going to get a positive value for k there. And that'll be the rate constant. So that's what we're doing here. It's really important that you can not only do it algebraically, but you can also do it graphically. And that the relationship between these two things is the line equation, y equals mx plus b. And they show you some examples of this and getting the slope. And so there it is. There's the slope, negative 2.55. When we plug that in, we're going to get the positive 2.55 like we have here. So just remember the rate constant's got to be a positive value. All right. Let's go on and do this while we're at it too. All right, so this is why it's really important for you guys to plan to take physics. You're doing half-lives. So what is a half-life? That means that what is the time it takes for the initial concentration to drop by 1/2? So for look at this right here. The when is the concentration half of the original concentration. So we plug in for concentration at time t this, that, and that divide out. You get T1 half equals 1 over K, ln of 2, because the 2 is in the quotient of a quotient. So you're taking the ln of 2. The ln of 2 is 0.693, and the K is down here in the denominator. And so there it is. ln of 2 is 0.693, and there's where they're showing that. Okay. And so you need to memorize that equation right there. What's cool about the half-life of a first-order reaction, you don't see any concentration dependency. You don't see concentrate. I mean, you got to have the substance present, right? But it's not like dependent on what is the initial concentration. And you go, why do I need to know this? Well, a real-world example is you've created uranium waste from a nuclear reactor. And you would think that, well, maybe if I pile it all up in one place, it will decay faster than if I spread it out in different places. Doesn't matter. Uranium decays in a first order process, so it doesn't matter whether it's little concentrations of uranium or large concentrations. Actually, these would all be the same concentration if they're pure solids. It doesn't matter, concentration. So it's going to take whatever it's going to take for it to decay. So that's the downside of uranium fission reactors, is that we have to have a place to store this radioactive waste for a long time based on its half-life. It's not the worst thing. I mean, with this global climate change that we have, where we're releasing a lot of CO2 into the atmosphere, that's detrimental too. And so we may have to designate places that are dead zones, that is where the uranium's going to be stored, but at least we're not generating more fossil fuels. Yeah, we are generating fossil fuels to harvest the uranium, but it's still less than all the cars and everything else. So just keep that in mind. So that's the thing about a first order reaction. It's the half-life is concentration independent. All right. So I believe we are going to stop here for sure. Let me make sure. I'll let you look at that one just to show I'm not going to do this, but you can do that one. All right. We'll stop there for this video, and then I'll talk about second order reactions, and we'll pick up on that on the next video. Thanks.